So, hello everybody. Some of you I've already just seen in my previous talk. My name is Neil MacIntosh. I work at Microsoft, where I am lucky enough to lead the C++ static analysis team, some of who are sitting in the audience here, good people that they are. You have to bear with me a little bit. My brain's still running through the last talk I gave, the things I feel I said wrong or forgot to say, so I'm going to try and push that away and talk to you now about a few good types. And specifically, I'm going to talk to you about some of the types that are in the GSL, which was talked about in Bjarne's keynote this week, and then again we talked about in Herb's plenary session yesterday. And specifically, I'm going to talk about two types in the GSL mainly today, array view and string view. And these are not the array view and string view that are current TS proposals with the ISO committee. These are close relatives of those things and largely similar, and I'm going to talk about some of the differences and why they're there and so on. So a little bit of background before I really get into it, and the background is that we started working on these types some time ago. As Bjarne alluded to, there was a project at Microsoft where, if you saw my last talk, we've got a whole lot of annotations that we use for C++, and we wanted to move away from using those annotations in our code base. We wanted to move towards using types to represent information and to make the code safer. So this is where these things come from. We harmonized with Bjarne as we became aware of his project to rework the coding guidelines. And so this is partially why the array view and string view I'm going to talk about today are different from those that are up for standardization. So let's make a start. I stole Herb's slide because that's one of the joys of working with Herb Sutter at Microsoft, is you can steal his slides, and he's a really good speaker and really good at putting together slides. So look at this. It's got color, some of it's faded, there's boxes with callouts. This is stuff I can only dream of doing in PowerPoint. So this is just a refresher for those of you who aren't familiar with the string view and array view in any form in anybody's proposal of what an array view looks like and the ideas behind it and what it's supposed to do. So basically, an array view is a pointer and a length bound together in a type that tells both tools and other programmers, hey, I'm using a pointer to point to a contiguous sequence of elements, and there are length elements in that sequence that are safe to use. So we can see here we've taken the function on the left-hand side that used to have some of those horrible cell annotations we were talking about in the last talk, horrible but good, and we've turned it into using an array view instead. Array view is wonderful because it can take const things and be read-only, or it can take non-const t's and be writable. Array view is heavy iterators, and you can see that the code becomes simpler, and it lets us catch a bunch of things we didn't. As I say, you've already probably seen this slide in Herb's talk earlier this week, so it's just a quick refresher, popping it up on the screen so everybody knows I'm not talking about static analysis anymore. Reminder to myself, I'm talking about these types instead. Key things to call out, other than we using array view and what it is array view lets us catch things really nicely at compile time. So an array view can deduce the size of the thing it's being constructed on, if the thing happens to be a static array in particular. And it can say, oh, you only want to point to the first 5 elements of that array? Well, that's okay, because it's got 10 elements. We can work that out at compile time, thanks to the magic of Spinay and templates and all those wonderful things. And thanks to those same things, we can also make it a compile time error if you're trying to address 30 elements when we know there's only 10 in that static array. So for me, this alone is a huge win for shifting to these types. Right? Because if we look at the old code, you need a static analysis tool or a good reviewer. And good reviewers, it turns out, are hard to come by. If you want to catch the fact that you're just taking things and sending 30 off, thanks to pointer array decay, that's fine. Perfectly legal code on the left, just the wrong thing to do. Perfectly legal code on the right, except it's not perfectly legal code, is it? It doesn't compile. So for me, moving those errors to compile time is one of the huge advantages you get from shifting to these types. So it's just like a warm-up introduction to array view. Let's talk about how we got there. What were we trying to do? Safety by construction. Wonderful thing. As I said in the last talk, the cheapest bug to fix is the one you don't write. And that's cheap, and it's easy to not write because the compiler told you not to write it because the compiler refused to compile it for you. So that's what safety by construction is all about for us. We want to, where we can't catch you at compile time, we want to enable the static analysis tools to help try and catch you 5 minutes or 10 minutes later. And if we can't do that, we want to make sure that anything you could do using these types that would violate type safety or bound safety or eventually lifetime safety will kill your program. Fail fast, right? Because you did something wrong. Now, it turns out that for lifetimes, as Herb said on Tuesday, we can do it all statically. And so we don't need stuff that will fail fast on you at runtime. For type safety, we can do the same thing. For bound safety, and that's what string view and array view cover, and that's what we're here to mainly talk about today, we do have to have some runtime checks to keep you under control on the straight and narrow. We'll talk more about them later. But notice that one of my key goals here that I've stated is to maintain the advantages we have with C++. The fact that the language is wonderfully close to the metal. You can have a lot of efficiency, a lot of precision, a lot of control in the programs you write. We do not intend to compromise that with these types. I mentioned enabling good static analysis techniques, and these types do that. And I talked about that in the previous talk, and if you weren't there, maybe you want to go see it on YouTube, and maybe it has some more useful information on that topic. The key thing, which most of you will have heard by now, is that these types are all being developed in the open. So we have an open source repository on GitHub that contains our implementation. I encourage you to go look at it. It's far from complete and far from finished, and I welcome contributions and improvements to what I see there today. And that's part of the idea of opening it and sharing it with the community. It currently supports a bunch of compilers and a bunch of platforms. So we're fairly confident it's portable C++, but if you can help us verify that, port it to more platforms, find things that you don't like or are non-portable about it, please do so. So I just want to drill in a little bit on what we're trying to achieve with these types, and particularly array view and string view. So memory safety, we talked about the bounds profile. We talked about bound safety, not stepping outside the boundaries of allocations in the system. We have other features, like the lifetime profile that prevents dangling. So here we're really just looking at, if you've got a sequence of things, don't go before the sequence, don't go after the sequence, just stay within the range of that sequence that was allocated. We want to do that without using non-standard annotations. We want to do it with portable C++ in the type system. There's type safety issues here as well. These types aren't only about bound safety. They also try and help you stay within the sensible limits of types. Don't make one thing another when it's not. Don't do dangerous casts that can't be proven safe, that might let you access more memory than you should. These types need to be efficient. So our goal here is no overhead compared to code that was as safe and written by hand. Okay, so the key part there is as safe. We don't aim to be zero overhead compared to your unsafe code that might overrun a buffer. We'll be low overhead compared to that code. That's the goal. And I think perhaps underrated in some people's discussion of these types is that they offer a useful abstraction. They get people out of thinking about, oh, this is a string, this is a vector, right? This is a static array, and embedding that knowledge all through a call chain, the way that we do today. What they do instead is saying, hey, you're looking at a string, but you don't need to know how it's held. You don't need to know if it's in a MFC C string, or it happens to be a static array of characters on the stack somewhere, or if it's somebody's heap allocated null terminated string. That should be irrelevant to you if you're just reading it as a string, right? If I'm giving you some data, a sequence of bytes or a sequence of foos or bars, then you shouldn't need to know if I'm holding them in a vector or an array or if I made a heap allocation, whatever it is, right? You should just need to know you've got a view over some storage. Unless you own that storage, well, then you should pass the specific storage type. So they introduce this important layer of abstraction, and I think that's an improvement to people's programs. It's about being crisp in interfaces. Do you own this storage? Do you really care how it's stored? Probably not. Are you just using something? Yes, then use a view. So let's look at our version of array view a little bit and learn more about it. So array view is a view over a contiguous range of elements with a known length. You've probably heard that a billion times by now. It's the pointer and length equivalent. It's a value type. Think of it as a pointer. When you're thinking about how do I pass this thing, you pass it by value, right? Do you need to pass it const? Well, you can, but only if you want for some reason to prevent people repointing it at other things. And sometimes it's useful when you get a parameter to be able to take it and repoint it at something different, or repoint it at itself, but a subset of itself, and so on. So most of the time, you just pass it straight by value. And it should pass cheaply and efficiently when it's passed by value, because it is stored as just essentially a pointer and a length. These things should be moving fairly quickly across call boundaries. You use it to replace any time you're passing a pointer in your programs today, and that pointer refers to more than one object. Because pointers, in the world of CPP core guidelines, in a world of better structured C++, pointers only ever point to one object when you use them in your program. If you've got more than one thing, then you're using an array view, or you're using a container of some sort, or you're using a string view, but you're not using a pointer and a length, or a pointer and an offset. You're not doing pointer arithmetic. And we've got some examples down here at the bottom. Array views can have a fixed size, or they can have a dynamic size that's specified at runtime. My microphone's a bit dodgy, sorry. So the first example here is an array view with a dynamic size. It's just an array view with some number of integers, and you can ask AV1 for its length, and it'll tell you how many integers you can see in it. The second example there, AV2, is saying exactly the same thing as AV1, just a little bit more explicitly because it filled in the default argument with the default value. The third example, array view of int10, AV3, is a fixed size array view. And it turns out it's really useful, especially in systems programming, to be able to talk about fixed size buffers. Why? Because it's really, really efficient to know that a buffer is a certain length when you're passing it down a chain. Plus, as we'll see in subsequent slides, if you have an array view that has a fixed size, you're only passing the pointer around. The type system remembers the size for you. You don't need to store it in the array view anymore. So that means you can be exactly the same calling overhead as you used to have when you were just passing a raw pointer and just assuming in your calling code that it had 10 elements. So that's one of those, hey, we can get here with zero overhead over your old code points. It seems obvious, but I'll just state it up front because these types can be confusing when you first encounter them. Array view, string view do no allocations ever. They are just views over existing storage. There's nothing you can do with them that will go and cause a heap allocation. Okay, so these are truly value types and truly low cost. Their size is fixed after construction. So if you point an array view at 10 elements, whether it's a fixed size array view or whether it's a dynamic array view, if you tell it your size is 10, then its size is 10. And that's it. It's an important property because it helps optimization, as we'll see later in the talk. It's also, perhaps more importantly, it's a useful property because it helps people conceptually. This array view, you can't resize it, right? You can get a different array view from it on a smaller view of that range. You could even reassign it to itself, but at that point you changed it, right? You generated a new array view at that point. So once you create an array view, its length is fixed. And the part that scares everybody, scared me when we first talked about it, is every access on an array view is bounds checked, always. No exceptions, no way out. And you violate those range checks, you fail fast. It's a bold statement. Let's see how it holds up as we walk through the talk. Code. Enough talking, make you all look at the colourful fixed size font. So if you went to my last talk, you know I have a passion for putting up real-world code examples simplified into toys on a single slide, and I tend to do so somewhat badly. So here's another example. Hopefully this one has slightly fewer mistakes than the last set I did. This code here is about reading some data in a network context. It's pretty simple. We get a packet in a buffer, that's called packet, and we get told how long our packet is, and then we want to read out the actual objects that were transmitted over the network in that packet. And we know we're going to get a foo and a bar, so we make sure that the packet was long enough and contained a foo and a bar, and it does, good, otherwise we return -1. And so then we go and we get a pointer to the packet, we cast it to the foo type, and then we can set the values of that packet, and it should be called write perhaps rather than read. See, I told you there'd be a mistake here somewhere. We can write to the packet, put our foo in, and then we can write to the packet and put our bar in. And to do that, we just do some pointer arithmetic, right? Because that's the way we do things. Right? Pointers are great and they're safe. So we just move our pointer along a bit, we cast it because casts are great, right? They never go wrong. And then we shove some of the bar fields in, and then we move the pointer along again, and we cast it to a fuzzbuzz because we need to write fuzzbuzz in there. We write some of those fuzzbuzz fields into the what? We didn't check for the size of fuzzbuzz back at the beginning of the procedure. So now we are potentially overwriting packet because we were so busy writing our fuzzbuzz. Now, seems like a toy example, but this is essentially the root cause behind the Ghost vulnerability that was big early this year. So Ghost was the very same sort of problem, but hidden by a whole bunch of data conditions. At the end of the day, somebody was doing an allocation at the top of a routine and saying, oh, I need all of these address fields. Do I have enough room for them? Yeah, I do, otherwise I allocate enough room for them. And then down here, a couple of hundred lines later, I'm going to write those address fields. Unfortunately, they weren't the same set of address fields between those 2 points. There was more down the bottom than they were up the top. So if you crafted your data right to the getnet hostint or whatever it was that contained the actual code, great, you could do an overrun. And that's exactly what we've got here. So fantastic, this is old, somewhat C-style code. How can ArrayView help us with it? Well, like so. It looks surprisingly familiar, surprisingly similar to the previous code. And this is one of the advantages we see for these types in the GSL, is that they are incrementally adoptable. You can change code without having to completely rework its structure, but you can gain the benefits of the types nonetheless. So in this example, I've taken a few liberties and added in the occasional like const expr or something to try and make myself look more modern than the original C code. But really, it's doing the same work up the front there, right? It's still making the same mistake. It's saying, hey, did I have enough room for a foo and a bar? If I didn't, return -1. And then we write the foo, but now we're doing something really different. And no, I'm not talking about the auto that makes me look cooler there. What we're doing now is we're saying we got an array view of byte in packet. So byte was non-const, so again, I should have changed this one to write to, but at least my mistakes are consistent on my slides. So we have a writable view over a contiguous sequence of bytes. It's not fixed size, so we know we can ask packet its length. And that's exactly what we do. Packet length, are you long enough? Okay, if not, I'll return -1. And then we call the asArrayView function. You can only do asArrayView on an array view of byte in this way. And so what it'll do is it looks and says, oh, is there enough bytes to materialize one, notice the one there in the template arguments, one instance of a foo out of these bytes. Now this is a dangerous operation, right? Casting just some bytes into a foo. But if you're writing something that's reading bytes off a network, you're going to have to do that sooner or later, right? So how do we help you in our type with this dangerous operation? Well, there's one way we don't help you, and that's already been pointed out in a very helpful issue raised on the GSL, and that is we should check the alignment of the bytes against the alignment requirements of the type. And so thank you very much to the person who's reported that issue, and I look forward to the PR that's going to fix that issue in the GSL. It's not an insoluble problem, and isn't that the wonderful world of open source? The other thing we do, though, is we say, yeah, are there enough bytes to fit the foo? We should also check the alignment. And we say, is foo a standard layout type? Is it okay to just cast bytes into a foo, in other words? Because the standard tells us when a type can or can't be treated that way. And so if you meet all of those requirements, and the magic of Svinay and templates help us enforce those requirements, then that code will compile and you can get one foo from your byte array. And you can put it in your auto foo, and then you've got one foo, so you know you can safely index into your array of foos of length 1, and you can start writing its fields. Fantastic. We do the same thing for the bar. We do something else first. We call a function called sub. And sub takes a length there. What sub does is it says, I want a substring, or a sub-array in this case. I want a sub-part of your array view. It starts at some location, and then it has some length. And so in this case, we're taking advantage of a default argument to say, well, we should have a 0 there. It's another bug on my slide. we say sub size of foo. So we want to just take a chunk of foo bytes. Sorry, it's not a bug on my slide. I'm confused from doing 2 talks in one day. This is actually doing the correct thing. What sub is saying is it's saying start size of foo bytes in to the array, and then read everything up to the end. We're using the default argument there, which is the length to read. So we're giving it an offset. We're letting the length default to as many bytes as are in the array view. So we're basically saying throw away the foo at the start, give me just the bytes at the end, and it doesn't modify P, it returns you a new array view, which we assign back into P because, it's convenient to have less parameters around the place. So we're just shuffling our array view along in one line. Nice and simple. And then, of course, we do the same as array view magic, get our bar. We do the same thing with bar, and we then get a fuzz bars, and we write the fuzz bars. So we've made the code better, but it's still got the bug. But now it's safe. Why is it safe? Because it dies as soon as we try and do as array view fuzz buzz. Because if your fuzz buzz doesn't have room, well, you're not going to get back that array view. You can't get the as array view fuzz buzz to work. It'll compile, but it'll blow up because it does a range check on the number of bytes. So we improved the code. Let's talk about some of these safety features of array view for a moment. Now, I'd mentioned type safety and type conversions earlier. And so as we do this sort of Cook's tour of array view, we have a limited set of conversions array view will allow. So you can go from a type to a const version of that type. Seems a pretty reasonable and safe and hopefully harmless thing to do. What you can't do is change types. And that makes sense because you'd be changing the size of the storage, you'd be interpreting things in a different way. Array view can't know if that's really a safe or a sensible thing to do. If you want to do that, if you really think you need to do that, it's all safe and the right way to do it, maybe turn it into some bytes and then ask array view to give it back to you from bytes. See if array view agrees with you then about the alignment and the standard layout characteristics of the types you want to move through. If not, opt out, do it manually, use a suppression. And there's an example of our conversion from byte to T, which is only done when your simple layout type and alignment is right and all those other characteristics are met. Part of the safe conversions array view has in its repertoire of things it can do is it constructs correctly from all the containers that you think it should know about. So it constructs from static arrays, it constructs from std array and vector and anything else that seems standard and it's likely to encounter in its life on Earth as it moves around. You should also be able to take your own types if they have storage that is contiguous in a sequence and you think could usefully be seen as an array view. You could fairly easily write a conversion operator that gives you an array view from it. And so then a lot of calling code can go unchanged if you change the signature to an array view, which is a nice thing to have. When you have fixed size array views, you get a very nice safety property, which is the type system can do some algebra for you to work out when things are safe and when they aren't. I find this slide extremely confusing myself because it's got numbers on it and it's got comparisons between numbers. Both of those things I find difficult. So I'm going to try and get it right as I go through it. So if we have a fixed size array of 4 ints, which we've declared at the top and then created a view over, which I've usefully called AV4, we can declare a new array view over that same array that's only 2 elements long. It seems a perfectly safe thing to do. We're not going to overrun it. We're not going to underrun it. We just want to look at the first couple of ints. Fair enough. So that's fine. And we can assign AV4 into AV2 if we want. Now, they happen to be pointing at the same thing in this case, so it would be pointless. But what I'm trying to demonstrate is I can go from a bigger fixed size array view to a smaller fixed size array view because I'm not going to overrun anything. And maybe I do just genuinely want to look at the first 2 elements. It seems a reasonable thing. I can't go the other way. So I can't assign my 2 integer array view into my 4 integer array view, which is in the middle there. It just won't compile. So it stops me doing something that would require me to overrun a buffer. And on the last line there, we see that I can go from a fixed view to a dynamic array view. It's quite useful in some contexts. What I can't do at runtime is go from a dynamic one to a fixed size one if the dynamic one isn't long enough to meet the requirements of the fixed size one. So as long as AV dyne has 4 elements, then we can assign it into AV4. In this case, it doesn't because I initialized it with 2 elements from AV2. So a runtime bounds check comes in and says, no way. So again, we're safe. These are nice features. And in fact, that last line is the only one with a runtime check, which is one of the nice parts of this. Let's look at more examples because we can't get enough examples. This example comes, again, courtesy of the Microsoft codebases I've worked on over the years. Real code condensed down, pretty reasonable code. Okay, it's got some cell annotations in there. What I think I like most about this code is it's got a very special type of contract in it, an invisible contract. It's my favorite type. And the invisible contract is, if you just give me a pointer and a size for a count for the pointer of -1, which is not even really a valid value for a size t, but I guess. Anyway, if you do that, I'll do a strlen on it to work out how long it is. Awesome. Thanks for making that invisible contract, because what you've done is embedded a nice perf cost in your routine that's invisible when you look at its signature anywhere else. Fantastic. That aside, the routine then goes through and does something pretty reasonable. Obviously, it was a little bit larger in the original, and I've snipped quite a lot here, including a lot more Hungarian than you can see there on the screen, and a lot more braces. But it's pretty reasonable. It's looking for the ampersand and trying to turn it into a more reasonable version of ampersand, and it calls the function at the top of the screen, write, to do so. And write has a similar signature to write XML, and we can only conjecture about whether or not it has a similar invisible contract behind it. There is a bug in this code. Can anyone see it? Nice, thank you, yes. Whoops. We did a size of a string. Now, that may or may not be a very serious problem. It depends exactly on what write does inside, right? So it may just mean, maybe you just write a null character out into your output, and maybe that's okay. Maybe you don't, maybe you check for it, maybe you don't. Who knows? It's not good either way because it's not meeting the contract that the cell specified, which is, you're going to tell me how many characters to write from this thing here. And I don't think the people meant to write the null character as well that comes with size of. And of course, if we changed it to wide characters, size of would be entirely the wrong thing to say. So, how can we rewrite this? Well, happily we can rewrite it using our other type for discussion today, which is string view. Now here I'm using one of the aliases we've got predefined in GSL for string view, CString view. And CString view is a string view of const char. So it's a read-only string view, for those of you wondering what that is. The nice thing about passing a string view is we don't need the length parameter anymore. Everything is self-contained in the string view. So if you were writing a static analysis tool, as I know everybody always thinks about doing, because it's such a cool thing to do, said the static analysis guy, here we needed Sal to be able to work out the relationship between the integer we're passing in and the pointer we're passing in. Here, the type system makes it really obvious. These two things are bound together in a vocabulary type. And also, the data that's accessible from that pointer, it's string data, right? It's a specific type of data. And that helps static analysis tools reason about what's going on with it. So the wonderful thing about passing the length in all the time and requiring it is we don't have a special invisible contract anymore. We can get rid of our potential perf hit and the magic contract that people might rely on, and then if it gets removed in maintenance, suddenly find their code explodes. We don't need it anymore. The length is always already measured when you enter this function. And so I really like this property of string view in particular. It applies to array view as well. But you know, if you look at large code bases when they pass around null terminated strings, people are always in a constant state of confusion. Do I need to measure the length of this null terminated string I just got? Or is that already contained accurately in this parameter that came over here? Or is in this structure over there? And that state of confusion causes people to do lots of strlens where they don't need to. Or write interfaces where they say, I don't know if I can really trust that you've given me the right length, so I'll remeasure it again, and then I'll pass it down to this guy, and he makes the same assumption, so you get like 15,000 strlens going through this enormous call chain as you go. We don't need that anymore. We always get the length passed along with the pointer. And then I've done minimal changes to the loop because I wanted to show that these types are incrementally adoptable. Okay? I'm pretty sure that given we're all CppCon attendees, everybody's looking at this thinking, he's a bit of a loser, he's still using the while loop, why isn't he using ranged for? Like that would be a much cooler thing to do, especially given he's obviously calling some iterators here with text begin and text end. You're right, it would be cooler to do it that way. Oh, and I did. But before we go into that, I wanted to point out that we can make minimal changes as we go through this. And that's an important property when you have big legacy code bases and you want to get the types in first to get rid of the annotations, in my case, maybe not in yours. But you want to get the types in first to improve safety, improve interfaces. You maybe want to make minimal changes in the body to make people feel comfortable with the types as they learn them and adopt them. And so in this case, we can just change the while loop to use iterators. But the nice thing is, this iterator is bounds checked as we walk through the loop. So there's no way we can ever get all of that ceremony we had at the bottom here about making sure that we move through the text and the length and one's minus, one's plus, got to get that right. We don't have that ceremony anymore. We just say, yep, just keep moving the iterator, and we know that if we ever do make a mistake, it's going to die, fail fast for us. Dereferencing the iterator there to check it against the amp character. It's now bounds checked. And we can be really safe and explicit when we call write to pass the new value. We don't have a size of in there anymore. We're making a call to a function called ensureZ. So we're saying this is a null terminated string. So we like Z for null terminated strings, so we put it on the end of the ensure, or is it Z? I can never tell. I've moved Z versus Z pronunciation districts, so I try and use both alternatingly all the way through. And it matches the fact that we have some type defs in GSL for null terminated strings. If you still need to use them, we'd prefer you use type aliases for them now. And the one reason to use type aliases for them is it makes them really obvious, again, to both readers and static analysis tools. We can tell, oh no, this is still a null terminated C-style string, just a pointer. There's nothing I can do about it because I have to pass it to an OS API or some piece of legacy code I'm not allowed to touch. But you can use a type alias and still remain API compatible with that stuff. The nice thing about the type alias is it's called ZString in the char case. And I like ZString because when I talk to Gabby Dos-Reis, who has a strong French accent, I don't think he'll mind me pointing that out, he often says ZString when he's talking about things. I feel less bad making that joke when you're in the room, Gabby. Thank you. So ensureZ says, I'm using a null terminated string, and so it returns a string view. And so it will do the strlen for you. Now, a strlen on a constant string like that, in every compiler I know of, will become a constant at compile time. So fantastic. So that's a zero-cost way of manufacturing a completely correct length for that string and passing it to write. Nice and safe, and we're more explicit about what we're doing when we call write. I like it. But, move on, PowerPoint. I do like it more when it's written like this. Because here, you just can't get it wrong. Right? And that's the beauty of ranged for. I love the fact that ClangTidy does that. Is it ClangTidy that does the ranged for automatic fix-ups for you? I think anything that helps you move into ranged for when you can is a wonderful thing. So now, we can't overrun. We've got the extra safety of ensureZ there. Writing the single character is super easy as well, because we're just constructing an array view of element 1 and passing that on. And this is where bounds checking is much less of an issue. See before where we had these 2 points we were talking about bounds checking, where you were accessing the iterator and where you were incrementing it. Now, optimizers can do magical things, it turns out, and improve a lot of that for you and remove that cost. But why not give love to the back-end code generators of the world, right? Like Jim Radigan would love me to ensure more love for him and his team. And one way to do that, one way is to write ranged for loops that can't overrun, because it makes it much clearer to a compiler that there's nothing going on here that even needs a bounds check. If it needs one at all in there, it can hoist it out, do it once at the top, and then know that the loop is safe and do all the optimizations it wants to. And we will talk more about this later. So string view, let's dig into it a little bit. It's a view over a contiguous range of elements. It's like a pointer in length, its length. Does this all sound familiar? It should, because it's exactly the same as array view, and that's all it is, an alias for an array view of characters. So we declare basic string view to be just an array view type deft on char t. And then, as we saw in the previous example, got a bunch of helpful type aliases that give you the various W and C versions of those things. I tried to get the C and the W in the right order because otherwise there's like a Commonwealth countries joke there about toilets somewhere. So I'm pretty sure that's the right order. Pretty sure. String view does have some quirks. It's about strings. So unlike array view, people are going to want to do string type operations on it. You know, people always want to find something in a string. They want to compare two strings and they want to compare them with string comparison rules that might be different depending on what sort of character set you think is in that character type. They want to trim them a lot, especially trim off white space, one end or the other and so on. Current GSL implementation is lacking a lot of these features today. That's really a time issue rather than a design issue, and you shall see them arrive over the coming weeks. They do need to be free functions. When you're using a type alias like this, obviously we don't want to put all of these string functions on array view because they seem to make a lot less sense there. I think that's a pretty reasonable trade-off, but it's always an interesting thing to get feedback on. I don't know if I made it clear enough in the previous example, but string view is completely agnostic about zero termination. Okay? You can manufacture a string view from a zero terminated string, as we showed with the ensure z function, which we've got repeated down here at the bottom. Fantastic. But that should be a C string view, I just noticed, if it's a const char coming in. But you have to be explicit when you're doing operations like that. And string view itself, it doesn't make any claims about whether or not the data it holds ends with a null. Okay? It doesn't care. If you think null is a valid character to have inside your string, then put one in there by all means. If you want to have one as the last character in the string included in the length, well, you could put one in there, just don't use ensure z. If you don't. The point is string view carries its length around, so it doesn't need to think about null termination. I think null termination is one of the great danger points in the language, and particularly in the legacy, but it's not something we can get rid of very easily or overnight. They're everywhere in null terminated strings. So we have to interoperate with them, but we don't want to propagate them through this type any further. So this type says, give me a length. I don't guarantee you it's null terminated or not. It's your business to work out when you use a string view whether or not you want to put nulls inside it. Common to array view and string view, there are some operations which we touched on briefly in the earlier examples. First, last, and sub. And you can see that all of them are overloaded both in a sort of a pass the parameters in a template version, pass the parameters as actual parameters version. Reason for that is some of these are quite useful to do on fixed size array views or fixed size string views. And if the thing's fixed size and you pass the parameters as template parameters, then a lot of that calculation can be done at compile time for you. So it's checked that way. So you know by the time you compile, did I get my calculations on how to slice up my string correct? And you know it's not going to cost you anything as well. So we've got both those overloads for convenience and safety. And they do pretty much what you'd imagine. They give you either the first set of elements out of the string view, the last set of elements, or some portion in the middle of the string. And in every case, they return you a new view on the array or string. I use them interchangeably here. We never modify these things because their length is fixed once they're constructed. You can also arbitrarily create new subviews using section. Now, why is section different from sub? Section's different from sub because array view can do something else that I haven't touched on yet and is too complex for my tiny brain to discuss in a talk today, and that is it can do multi-dimensions. You can have array views, you can't have string views that are multi-dimensional, as Herb said on Tuesday, that makes my brain explode, but you certainly can have multi-dimensional array views, and when you have them, you want to be able to section them, you can stride over views of them and so on, and look at them in non-contiguous ways as well. There's a whole lot of functionality there that I won't drill into in this talk because I think 90% of the use of arrays in people's code is one-dimensional, and that's probably what most people are interested in here. But I do encourage you to go look at the interfaces there, ask questions. We've driven out some bugs and improved them in the past couple of weeks, but feel free to do more there. Other things I love about ArrayView. Let me count the ways. You can construct it obviously from a T-star and a size type. Doesn't sound super safe, does it? But sometimes it is the only option when you're dealing with legacy code. Sometimes an operating system or a library you're calling, something you can't control but really need to use anyway, is just going to give you a pointer and a length, and you're going to have to trust it. And as Herb said, this doesn't compromise the safety of the code you're writing that uses ArrayView, right? It's a trust point. It's a trust point you're going to have to audit, but it's a trust point. And so you can construct an ArrayView from these things, and it lets you be more compatible. It lets you leave an ABI interface that you can't change for legacy reasons or for ABI compatibility reasons, and just construct an ArrayView from the data that's passed to you there as the first thing you do, and then rewrite your code to use the ArrayView. It's what I like to call like improving the onion from the inside out, right? The outside is still that onion skin, but you've like taken away all the interior parts of the onion and replaced them with ArrayView. So you've gotten a lot more safety in your system, and you know that you've got these boundary points. Similarly, if you're going out to one of those boundary points, you can get direct access to the pointer that ArrayView holds with the data function. I would suggest you only do it for passing to legacy functions. You'll get a warning from our checkers if you use it. In the same way, you'll get a warning if you construct from a star and a size type. We're going to warn you and say, hey, it's a trust me point. And that's okay. You can document it, you can suppress it, but then you can go back and say, oh, this is one of these trust me points. I wonder if that's where the bug came in. And at point out here, you could use that suppress bounds type syntax for a particular warning message to do those operations. So let's talk about how these magnificent types differ from their cousins that are currently in the library fundamentals TS. Hopefully the ways are not too great. So one of the obvious ones for those of you who are familiar with the TS is we add the possibility of fixing the extents in each dimension for an ArrayView. So that was that fantastic int, 10 example of the ArrayView I gave earlier. We added the conversions to and from byte representation. And we do that because we've also defined a byte type in the GSL, which is a useful thing to have, we think, distinct from char, which is a character, not a byte. We added more constructors than the ArrayView TS has to support drop-in use with all the standard containers and variations of array that are in the universe that we know of today. And we also interestingly describe the length in two ways. We give you the length in elements, which is length, and we give you the length in bytes, which we call bytes. Some people have said maybe it should be byte size or byte length, and those are probably excellent pieces of feedback. Regardless of what it's called, it's a tremendously useful thing to be able to talk about an ArrayView's size in bytes as opposed to its size in elements. This really helps, especially where you have legacy code that likes to calculate things in terms of bytes, but then address things in terms of elements. It sounds weird, but I see code do it all the time. And anything that makes ArrayView more adoptable is a friend to me. Our ArrayView allows you to choose the size type that we use for measuring and indexing. So it defaults to size t, which seems like a reasonable sort of a default to choose, the standard size type. But if you'd prefer an unsigned short or an int64 or something else that seems to fit better your needs because you have a super large or a super small array, maybe you have pack structures on your platform and you want to make the ArrayView as small as humanly possible, then you can do those things. Part of the motivation there is, as I mentioned in my last talk, I think there's some other useful general purpose types like an array buffer that we see coming down the pipe in the future that have much less widespread applicability than an ArrayView. Everybody's always looking at sequences of things. Less people are doing sort of sliding buffer movements over sequencing of things. But when you do those sliding buffer movements, it turns out you often want to say, hey, I just want two unsigned shorts and a pointer, because that packs in really nicely and that data's never longer. So it makes for a nice compatibility story when you can say, hey, I control the size type for all these ArrayViews and all these array buffers I'm going to use. And thanks to the magic of templates, it doesn't cost us anything to do it, other than the insanity of the people doing the implementation of ArrayView. And we added first, last, sub. These are additional over what the TS has today. It just has section and stride and some of those other functions. How do we differ from the string view? Well, The biggest difference is we just see it as a type alias. Right? So the current proposal says, no, string view is its own type. We differ on the way we work with zero-terminated strings. The biggest difference is that the string view as proposed can't do mutable characters the way this string view can. And we think it's a real shame if you can't write through the strings that you're passing around in the cases where you want to write through those strings. So that's probably the biggest sort of conceptual difference between the two string views. And obviously we have the string-specific functions as free functions because we are a type alias, and they don't because they're a sort of concrete string view type. So we've actually used these a little bit inside Microsoft, our versions. And some things that we've noticed in the process of using them are, it's super easy to call a string view where you used to pass a pointer length because you just put some squigglies in and then everything's good. So that's that pointer length constructor, that's that interop story. So you can start using array views and string views very, very quickly in code that was passing a pointer length before, just through the magic of the uniform initializer syntax thing. It's really convenient. Similarly, a lot of loops, I mean, they should become ranged for, they should improve, but you can start by just calling length instead of looking at the length thing. Great. As I showed in my earlier example, you can take your existing while loop and just swap out the pointer magic and use an iterator instead. It's a great first step towards getting these types into your code base. We noticed, as I mentioned before, the bytes elements difference makes things easier to read. The one thing you really do want to do early on is have nice convenient wrappers, and they tend to be single line wrappers, for things that are legacy APIs. I've just named some of them there. I love the way at Microsoft we like to have like an equivalently named standard library function. Memcopy isn't good enough, we call it copy memory, and we change the order of the parameters. And zero memory, we do the same thing. It's awesome. But so you want to wrap those things pretty quickly so they can take array views, right? Because it's another step towards, oh look, it looks the same because it's overloaded and this wrapper just passes through at no cost, but nice incremental adoption strategy. So as we run down my talk, it's time to talk about performance. Couldn't push it off forever. Everybody wants to know, why are you pushing these range checks on me? How much am I going to pay for them? Do I have to get my checkbook out, or do I have to tell you to go home? Well, let's try and see. Remember, we're aiming for zero overhead here. Now, we've done some experimentation, and we've tried to start on a path of optimizing array view with our compiler. That's not available yet today. We're going to have to make some changes in the compiler to make this go the way we want it to, and that should show up in future VS updates. You should start to get compilers that'll do optimized code generation with array view. And on the way to shipping those things, and I'm not going to go into too much detail here, I think we'll be making some blog posts and probably giving some talks about how those optimizations work so people can understand exactly what you need to do to make these things really work well. And it turns out not a lot is the answer if you already have thought about the problem of optimizing range checks in your compiler, and many have. And I'm not going to show you assembler today, I'll just warn you now, because I don't want to steal Jim Radigan's thunder. That's his thing, and as he likes to say, they don't let him out the basement very often, so I want to give him more opportunities to get out, show his stuff. The key insights we had to starting down the path of optimizing array view is that the type system, and you must be so sick after 2 hours as I am of hearing how wonderful the C++ type system is, but it really is, you can leverage the information in the type system to make these optimizations. The semantics of a default copy constructor help tremendously with array view, which has, surprisingly enough, a default copy constructor. The semantics of a const global array view help you optimize accesses to that global array view. How? I'll come to that in a moment. In each case, these type system semantics are making it clear to the optimizer that what you're working with is not changing. And that's the key. So that for the optimizer, knowing that the value in the pointer part of the array view and the value in the length part of the array view are not going to change underneath it once it gets them via a parameter, or once it looks at them if they're a global, lets it make some really important assumptions. Even so, these things do emit range check type instructions, and some of them need to exist. Right? There are places where you're going to get a pointer and a length, and then you're going to use them, and the optimizer is going to have to say, I really do have to do the range check here. There's no, I did have to do at least one inside the function of this body. Luckily, our compiler was used to do the .NET native code generation. And so our backend has already had to do a lot of thinking about how you hoist and eliminate range checks in code, because it turns out that .NET is full of them. And so there's a lot of theory as well in the world of compiler optimization about how you do these optimizations. A lot of it we've drawn on in our backend. The nice thing is we get to use all that work, but look, we don't have garbage collection. We don't use the .NET framework. We don't have a runtime DLL that adds overhead. So we get the benefits of optimizing away range checks without the costs that the .NET people paid for. That's just a dig at the people I work with in the next office. You can just ignore it. It's really just for Andrew's benefit. He used to work with them. Let's look at a concrete example of how this works today. And this is a messy example. I'll apologize in advance for that. So this is roughly based on a benchmark, like one of the very simple benchmarks we use for looking at compiler optimizations. And that's the 8 queens, or 12, or 9, or 50,000 queens, depending on how many you want to run through it. Sort of classical chess problem. And it's solved in its basic C implementation using some global arrays and then some arrays that are statically declared and then passed to functions. And calculations are made between these arrays that are passed in and the global arrays. Who cares what the calculations are, and who cares what the benchmark's really doing? What we want to know is, where's the cost, and how do we make savings? What I have up here is the original, well, roughly the original C version of one part of this benchmark. So the important features to look at are, we've got a fixed size array type, 9 integers, and then we've declared a global of that. We have a function that accesses that global and also takes a parameter of the same size array type. And it iterates over. Len here, you don't need to worry about where it comes from. Let's just imagine, len's a parameter or it's calculated. But it iterates over for some number of times, assigning between A and glob, which is the global. Now, if you're an optimizer, this is code you love. It's incredibly easy to optimize this. We can see straight away the loops monotonically increasing, right? Every loop we go around, we just increase I by 1. And it's always I, there's nothing else that's going on in the loop. Trust me, even though you can't see the whole loop here. The compiler knows the address of that global array can't change. It knows what it is, so it can load it once, fantastic. It knows the address of the parameter, similarly, can't change, right? It's just been passed in once. So it can load the address of the global, load the address of the parameter, it knows you're assigning between them, it knows you're moving between them in the same way, it can do strength reduction, it becomes an incredibly small number of very efficient instructions once it's been optimized away. Fantastic. That's why people love C, I guess. Here's the array view version. So we still have a global array of 9 elements, and now we declare a const array view. And notice that the const array view tells us something about the array view itself. It means we know it's never going to be pointed at anything else during the program's execution. So we know the pointer value in array view, and it only has a pointer value because we used a fixed size array view here to match the fixed size array that was in the C example. We know that pointer value won't change, can't change during program execution. And so we can do all sorts of fantastic things, assume fantastic things about that address. We can even load it into like read-only pages and so on, so it can't be modified if we want. We pass an array view, again a fixed size array view in, so we've got exactly the same call overhead going on here. We're just passing one pointer in both the C example and this array view example. And here's the key part. The compiler knows that once P, that parameter, comes in, array view has a default copy constructor. So that means the value that P gets at the start of execution, that's the value it's got. It can't be aliased with everything else. There's no other function call you can do inside this function that can change the value of P. Awesome. So if the function itself doesn't change the value of P in any way, that means that pointer value is effectively constant for that function. Didn't even need to put const on the array view. It's just by definition. Fantastic. So we're basically at the same position we were at for the C example. We've got 2 addresses that we know don't change for the lifetime of this loop. The loop is making a function call, but it's a function call that's compile time evaluated because this is a fixed size array view. So we know that the function is still monotonically increasing, still has all the same properties it had before, the addresses are fixed as they were before, we can do all the same optimizations. All the same strength reduction, we get to the same number of instructions. Aha, you say, but what about that bounds check on the line where I put the comment? Now, because the optimizer knows these addresses can't change, and it's been told, hey, just check to make sure you never go more than 9 elements past the end, and the compiler can see, hey, I'm in the process of optimizing this loop, so it's optimized for just iterating 9 times over the, oh, I can throw away the bounds check. I know it's safe. I can prove by the properties of this loop that increases to a fixed size up to p.length, I can prove that those bounds checks are redundant, so it throws them away. Now, you can't always make that optimization, but it turns out you often can. In the cases you can't make that optimization, you can often hoist it above the loop and do the range check once. So what we have here is an example of a case where the optimizer can completely remove any costs associated with array view. So the abstraction becomes 0 cost in this case. And we think the cases where you do have a hoisted bounds check, if you're going to write equivalent safe code, you should be doing that bounds check anyway manually if you had a C equivalent. So I think we are well on the way to showing 0/low overhead use for array views in code with some massaging of a compiler to help us get there. So as I wrap up this talk, let me encourage you all to join in. Right? Come have a look at array view. It's there at the resource I've given you there. It's there open on GitHub. Look at the TS docs. See what you think of the differences. Improve it. Port it. Write your own array views. Write your own GSLs. Give us feedback. Give suggestions. Make ones that are better. The more, the merrier is my call here. And with that, I think I have a few minutes left for questions if anybody has them. Thanks.
Hi. So one of the things, well, first off, I've been a big fan of Vue classes for quite a while now. One of the things that bothers me about the library fundamentals version of StringView is the comparison semantics, which I believe make it unsuitable for use as a range with Eric Niebler's range proposals, because it compares character by character so that 2 string views pointing to different areas of memory can be equal. What are the semantics on views in GSL?
It's a terrific question. We don't have the compare functions spec'd out at the moment. So my answer is TBD from my knowledge at the moment. What I can tell you is we definitely want these types to be compatible with Eric's proposal, which I'm a huge fan of. So I think that's an interesting area to work down. I mean, we've shown Eric these types in our versions of them as we drafted them, gotten his input, so I think we'll just probably make the comparisons harmonious with ranges.
There was another question. The as array view function, is it essentially reinterpret cost? Is it bypassing the cost system of C++?
No, you're right. It is essentially a reinterpret cast. In fact, it just is a reinterpret cast at the moment. And this is one of these liberties you get to take when implementing these vocabulary types is, although that's obviously a bad thing to be doing, using reinterpret cast, it'll be suppressed in array view so that you don't get warnings from the checkers that look at the implementation. There are places when you implement those sorts of boundary fundamental types that you have to do those things. As Herb was saying, you have to sometimes open the hood to do something. It's in a limited place. You look at it very carefully, and then everybody else's usage is safe.
Just a correction. Array view has been pulled out of the fundamentals TS. The problem was multidimensional. We were not happy with any of the proposals we had. So the LWG would be very happy, and LEWG would be very happy to see a proposal that included multi-dimensional array manipulations that we felt were safe and useful.
Awesome. I stand corrected, and then look forward to bringing this to talk to the LEWG.
Yeah, I also had a wow. I also had a question about the multidimensional array views. Do you think that strides could be incorporated into them?
Indeed, they have been. I'm looking at the lady who incorporated them into our version in the past few weeks. You want to stand up, Anna, and just sort of there you are. Anna put them in for us, just in there. Well done. So yes, is the short answer. And I think we're out of time. I'm being told session is over. So thank you very much. Happy to chat after.